fixed window Kasai algorithm. The difference between the phase derivative in the Kasai algorithm was that in the Kasai algorithm we consider all the samples in the slow time. This I index represent the samples in the slow time. So we have signal x and y in the slow time, and we will use all the samples of x and y. And with that, we can obtain a ratio here, and then an arctangent, that is an angle of that ratio. That will be associated with velocity. The simple case of Kasai algorithm is when we use only two samples in the slow time, and we go back to the phase derivative, to this kind of expression. I think we talked a little bit about this too, right? Oh, the well filter, I think we'll stop here. We mentioned that the well filter will help to eliminate all the signals that may have a strong intensity but come from fixed positions. And for motion detection, for the Kasai algorithm or the phase derivative algorithm, we want to consider only the slow time signals, but after all this discrete signal has been eliminated. In other words, if we think about this as a slow time, at this z, we have a signal that looks almost constant. But if we check after filter, it's not completely constant, or around here. We see something that looks more or less constant, but here we see changes across this axis. Okay, so there is this effect of well filter that is necessary. And these are the slow time signals that we can process. X and y is in one step. X and y for each step. X and y of the slow time signal. Okay. Some disadvantages of the fixed window could be signal to noise ratio versus spatial and temporal resolution. In practice, phase estimates or velocity estimates in the slow time are noisy, and you need to average numerous estimates axially and estimates from several consecutive excitations. For example, we have estimation velocity. This is the depth. Every blue point here represents the velocity estimated with the phase derivative. You see m equal 2. No? M equal 2 is only two samples in the slow time. It's like the phase derivative. But with the Kasai algorithm, we have 50 samples. So we can use more samples. Estimate actually and estimate from several consecutive excitations. Yeah, exactly. We use 2 consecutive excitations, 50 consecutive excitations, or 250 consecutive excitations. So more samples in the slow time that come from consecutive excitation make the Kasai algorithm the estimates look more smooth, more constant, compared to only using two samples. We see a lot of noise. It's like the velocity should be, for example, 0.2 meters per second, but look at how this is changing. It's not 0.2 always. It can be 0.15, 0.20 something. It's changing a lot. one is better? Maybe something in the middle, right? Something not so noisy, and also something that is not completely using all the signals because it looks not so realistic. So it's, we use it to balance appropriate values. So typically in these problems, you practically test many changes in number of consecutive excitations used in the Kasai algorithm. Also, as velocity increases, imagine that this represents some movement of the particles. Red blood cell, for example, it's making change in the slow time, making change of the echo with different, at different times, at different slow time samples. So, analyzing these samples, we obtain a velocity. If the velocity is larger, this will be probably, we look with more change with different slow times. But we saw, right, if we calculate the fast Fourier transform, the derivative, Fourier transform of this slow time signal, we obtain some spectrum in the slow time domain that has some sampling frequency. And we saw, okay, this maximum frequency will be associated with the velocity of the particles that are moving there. And the problem is that here we are at the limit. What happens if the velocity of this particle is moving even more faster than this? It will happen that the spectrum will look like this, for example. And the symmetry part, maybe we look like this. So in total, we see there are some, for example, this part. At this frequency, we have these two values. So we can notice that there is some combination of values here. So it's difficult to say what is the maximum frequency here. Because we cannot say that this frequency, for example, because here looks zero. Okay, so this is equivalent to one problem that we had in digital signal processing. One problem when the sampling frequency was not enough for the signal. What was this problem? The problem when the sampling frequency is not big enough to capture the effects of the slow time signal, in this case, the aliasing. This is equivalent to the aliasing. So it's like between the slow time signal, there are some periods, TPRF, repetition frequency. This TPRF is associated with the sampling frequency in slow time. And this sampling frequency is associated with a maximum frequency possible to be calculated, that is half, right? Remember? It was like the maximum possible frequency that we can capture is half of the sampling frequency. In other words, the maximum velocity is associated with the half of the sampling frequency that can be captured appropriately. So if in practice, this recursive start moving faster than right now, we need faster also sampling frequency or a smaller TPRF. So we need to sample more with shorter times. So that's a requirement. So what is the meaning of that is that if we fix some sampling in the slow time, we will have some maximum frequency possible, and if there's some velocities moving up more than that, the estimation won't be correct. So we may have some errors in the Doppler image. this is one example. What happens, for example, when the speed increments? So here it's faster, but if we look at the position in this depth time, we see that the amplitude look constant. So obviously, it's not capturing the correct frequency. Right? Here is like static position. This is like static position, but that's not true. Like here we needed an intermediate signal. So maybe half of the TPRF would be enough in this case, but like this is not enough. The reflectors appear to be stationary even though they are moving faster. And as you know, one of your friends said, that's Alice. The Alice is the phase, the fact that the phase is periodic with 2π, and the Kasai algorithm is equivalent to measuring samples of the echoes at the sampling frequency FPRF. Therefore, the maximum speed that can be detected with the Kasai estimator without including aliasing is half of the maximum. What was the relation that we saw for the Kasai algorithm? The maximum velocity will be c over 2 divided by f0, and the native frequency, that is FPRF, divided by c. Basically, this is the relation between velocity and frequency. Right? I think we had this equation before, right? In the simple case, I think. Say right or not? C over 2. Yeah, I think it's equivalent, right? It's equivalent to this expression. Okay. What is the phase derivative here? Oh, I think we got this, right? So with this, it's equivalent, right? Something. think there's a term too high that is different, right? I think. Let me check. I think we should be fine. Yeah, let me check that. Okay, I think here I'm using some Python. I will check that later. It should be the same, right, as before. We said that the maximum frequency or the maximum velocity is associated with the velocity 4 pi f0 CPR. Yeah. Let me check this expression later. Okay? I will check this expression need some pi or not. I will write that later. For now, let's consider this expression. Okay, let's check if this is okay. I think maybe it could be okay, but maybe I'm missing some factor of that. Okay, I don't want to lose more time with this. Okay. So, however, no, FPRF cannot be increased indiscriminately, since for consecutive echoes not to overlap, it's necessary that FPRF is less than C over D0. Okay, it's like no. Due to the aliasing, no, we are saying that okay, we would like to have the TPRF, no, the period between different excitations, as low as possible. So we have this as low as possible. The FPRF will be very large, which is that's good to avoid aliasing. But if this is very small, the problem will be we have no user and we have some vessel. When we send the first pulse, we send this pulse, and then we need to wait at least the time to reach what? To reach the vessel, and even at the last part of the vessel. If the vessel has thickness, the 0 and D, we need this echo to reach the last part of the vessel and then go back. So, and the total distance. In this case, well, I mentioned D0, but it's really D0 plus the thickness of the vessel. Here, aliasing occurs when the flow rate is greater than that allowed by the FPRF. And increasing FPRF allows to eliminate this effect. It's like some velocities around here, in these positions, are detected not as a maximum, but instead as a negative, not minimum. It's like the other way. This, why? Why this appeared? Because the FPRF in this case was not big enough, to capture this velocity like in this area. So when we increase that, yeah, we get more uniform. So even here, we have to see some points not correct. Okay, so FPRF larger is good. That we need to take care of this. Right? Okay, we finish with this slow time. We get a lot of this. This is important part of Doppler, but also variable window is important. It's probably the most simple way to analyze this problem is it consists on using correlation between with the window. The window is fixed at frame 1, and the window scrolls in frame 2. The advantage of it that does not suffer from aliasing, has a better signal to noise ratio, but the disadvantage is probability of false detection, and high computationally cost. Now imagine, okay, now we have in the pulse wave Doppler case, so we have, for example, all this signal echo in the excitation 1, and all this signal in the excitation 2. Now, only looking at this, what is on here? No? It's like, okay, for this position, we choose one block, one window, and try to find the structure of this echo in this window, the same as what is the position that the displacement of this window, how much is displaced, and that can be calculated doing the correlation of this with all the possible windows, like this window and this window, this window and this window. If we do the calculations for all possible windows, there will be one window that matches almost perfect the structure of the waveform. When it matches perfectly, it means that this echo really displays to this position. And with that displacement, that's the delta t, right? The delta t, I think it was in some previous. No, some previous slide that we saw. Just calculating the delta t, how much the signal was displaced. Knowing the TPRF, knowing the velocity c, we know the velocity of that particle in that position. As I mentioned, this is easy in this case, right? When there is only one echo, so we can see this is where it moves, and how much time in the echo is changed. But when there are more signals, it's difficult. Like this, we cannot calculate that unless we use correlation. Yeah, so I say, it's difficult, but if we do that for every window, we can have one best possible displacement. And we say, okay, for this, it moves this delta time. We just measure what is the delta time between these two. And with that, we estimate the velocity. And we repeat that for all the positions, all the blocks. For every block, we calculate the correlation with all possible blocks here, and we will see. For this position, we move some. For this position, we have another delta t. For this, another delta t. And with those delta t, we calculate the velocity in that band. If you see, we are doing this correlation in the fast time. This is the fast time. And we are doing it, look at it, right? With all possible, right? All possible blocks. For every window here, we have many calculation correlations. Here we can have many samples. This signal can have many samples. We discretize this. So calculating this with this is a convolution, equivalent to convolution, or similar. So we have many operations, multiplication operations, sum operations. If you remember from this field, we can calculate how many operations are, or even calculation of convolution in computational systems is done the other way. It's like we calculate the Fourier transform, multiply the Fourier transform, and invert that Fourier transform. And that's how the convolution is calculated really in computational systems, instead of doing manually the integral. So there are many operations associated with every position. So with the slow time, remember, we use all the samples in one position and calculate the one Fourier transform, and that's it. Identify the maximum frequency. In this case, no, we have many operations. So that's why high computational cost. And also this probability of false detection is like maybe for some reason, for this block, this was the maximum, or this was the correct displacement. But I don't know, for some reason in this block we calculate a numerically a larger correlation value. So for this position will be assigned this displacement instead of this correct displacement. So that could be too, because we tried with many correlations possible. Maybe there could be some error in the detection of the peak. The function of correlation remember how was that? It's an integral, right? Integral. And an integral in the, for example, the domain. And we will see that, for example, for this block, correlation almost zero. And we calculate for all possible blocks correlation. And all of these points correspond to the correlation between this and this window, this and this window, this and this window. So there will be one window that will get like a maximum correlation, and that again the displacement that we use for calculating the velocity. Yes. Pulse wave Doppler traces from user selected regions of interest are also displayed as 1D graphs in ultrasound scanner. The tracer showcases the pulsating nature of blood flow. Okay, this is just, what they are saying is that, okay, if we have this Doppler, for example, in one moment, we calculate this kind of image, where the red means some direction in the velocity. And if we just plot this region for different times, we will see how this is changed. Because the blood flow may change direction during this process in the heart. We have different systole, diastole, different movements. So the velocity, you can see how change with time. So this is just another representation in one specific region of the vessel. Yeah, sometimes people will associate some disease with, for example, what is this period, or how fast this fall. They just analyze this signal as the way they want. But we obtain this signal from the Doppler, from the Kasai algorithm, for example. And also the power Doppler method also is something that devices have. This method discards the phase information to gain greater sensitivity. In other words, directional information is lost, but the smaller vessels can be visualized. It's primarily used to visualize the vascularization of organs. So this power Doppler is more simple than the Kasai algorithm or the phase derivative algorithm. The principle is the same. First, we have our slow time signal for different depths. After applying the wall filter, so we have only the moving parts. And for this depth, we have the a slow time signal here, no? RS. For this position, we have the signal RS. No? This signal has many samples, as you can see, many samples. And we use sum the square of the sample. Just take the absolute value of the sample, square that, and sum that. No? And that value is, we assign the variable P. And we will do that for all the columns, all the letters, for all the letters. So we will have a vector of P. That P is related, no, to the absolute value of the signal square. It's related to the power or intensity in general, no? When it's square of some voltage, magnitude, is related to power, intensity, energy. But doing this square, we lose information about the sign, no? The sign of this, the phase, and the direction. So there, this very simple approach is take the signal and square of that, or take the signal and separate it in real, no, imaginary, no, part, and from X and Y calculate, no, the R tangent, no, imaginary and real part that do the Kasai algorithm, phase derivative algorithm. So yeah, two ways to do that. Right? Use the typical Doppler, or use power Doppler to calculate this. Which one is better, right? It's like at some point, some people say, okay, let's just do that, right? And they also get some nice image like this. Well, in this image, or in this image, typically represented in this color map, no, hot color map. No? We just see some changes, right? And these changes here represent maybe some vascularization, right? In this, looks like abdomen, probably a liver. Mentioned, but probably it's a liver. And we can see, right, that inside the liver, no, there are some regions that have some vascularization, some blood vessels. So maybe with the Kasai algorithm, we will detect only this part, something close to this part, but with the power Doppler, we will get more detail, no? More information about other vessels inside the organ. No? Because organs have small vessels, there is not only one big one, right? There are many smaller parts. Yep. For example, no, when we think about cancer, no, in these organs, no, cancer really are masses that need more energy, no, some mass and more energy, and so generate more blood vessels, for example, close to that cancer region. So one power Doppler would help to observe. Right? There are some strange, some region that looks like have many vessels, may have something related with some malignant tissue. And something related with this power Doppler, no, is another application, no, of this power Doppler is perfusion imaging. In this context, perfusion imaging is like the heart, for example. The heart, how much blood the heart can, no, or in this case, what is the myocardium? En Spanish, el miocardio. ¿Qué es el miocardio? Se ha llevado en Cayetano, por o nunca.
Pablo, eso. La capa del corazón.
Cardio, no? Related to the heart, right? But myo, what's that? Sí, ¿no? La membrana. Sí, realmente, y el músculo, ¿no? Es músculo de. Esto realmente es el músculo. this case, the myocardium, if there are some blood push through the myocardium, we will see changes in Doppler image. Doppler image will look like all these vessels in the myocardium are filling with, with blood, with some with blood, and we can see that how the myocardium is filling in this in some process. Or in other words, here's a perfusion imaging with contrast agent. In this case, we haven't talked about much about contrast agent, but contrast agent can be some liquid that is injected in the bloodstream, in the blood, and that will increase the intensity of the slow time signal. All the signals in the blood flow. So we can see how that is increased. So the contrast agent increase that intensity. And it's like we can see with different images how this myocardium is filling with more blood. And some people try to say that, okay, how fast this fills with blood to reach a maximum intensity is associated with the state of the myocardium, for example. And they try to describe that the state, analyzing, for example, how long it takes from low intensity to maximum intensity, to reach this maximum intensity. Maybe for some healthy people, it's quite fast. But for people that is very old, has disease problem, maybe this will be very slow. So just analyzing in this case, how long it takes. So people try to find relation between healthy and disease. But it's just an use of the Doppler image. So how you use Doppler image will be, that will you can find in paper. Right? They use different ways. At the end they use Doppler or power Doppler. Or other ways to improve this image. Right? It's not the only way to do power Doppler. There can be other ways. Obviously we won't see here. But you can read in some paper if you're interested. Okay. We finish.